Welcome to today's paper reading. Today's paper is titled, Leveraging Large Language Models for NLG Evaluation, Advances and Challenges. This paper was published on the AR14 preprint by Zhen and colleagues from SKLSD Lab, Beihang University, and other esteemed institutions. This paper addresses the evolving field of natural language generation, NLG, evaluation, particularly the introduction of large language models, LLMs, which have opened new avenues for assessing content quality, such as coherence, creativity, and context relevance. The paper aims to provide a comprehensive overview of leveraging LLMs for NLG evaluation, an area that currently lacks a systematic analysis. To address this, the authors propose a coherent taxonomy for organizing existing LLM-based evaluation metrics, offering a structured framework to understand and compare these methods. The paper also critically assesses various LLM-based methodologies and compares their strengths and limitations in evaluating NLG outputs. By discussing unresolved challenges, including bias, robustness, domain specificity, and the need for a unified evaluation approach, the paper seeks to offer valuable insights to researchers and advocate for fairer and more advanced NLG evaluation techniques. The introduction of natural language generation, NLG, with large language models, LLMs, has significantly advanced AI-driven communication. These models, driven by deep learning and extensive data, excel in text generation across diverse applications. However, traditional evaluation metrics like BLEU, Rouge, and TR, which focus on surface-level differences, often fail to assess semantic aspects adequately. This limitation necessitates more robust evaluation methodologies. LLMs offer promising solutions with capabilities such as chain of thought and zero-shot instruction following, providing more sophisticated and human-aligned assessments compared to traditional methods. Figure 1 illustrates the use of large language models, LLMs, for natural language generation, NLG, evaluation. The key strategy involves instructing LLMs with prompts to evaluate generated text from various aspects, either with references and sources or not. This approach addresses different tasks and goals, providing a more sophisticated and better human-aligned assessment compared to traditional methods. The formalization of NLG evaluation is presented as E equals F, H, S, R, where H is the hypothesis text, S is the input source, and R is the set of ground truth references. The evaluation function F can be instantiated by LLMs. The paper categorizes NLG evaluation along three primary dimensions: evaluation task, evaluation references, and evaluation function. The evaluation task includes diverse tasks like machine translation, text summarization, and dialogue generation. The evaluation references are classified into reference-based and reference-free scenarios. The evaluation function can be either matching-based or generative-based. Generative-based methods include prompt-based and tuning-based evaluations, further divided into subcategories such as score-based, probability-based, and advanced evaluation protocols. Figure 2 illustrates the two primary types of NLG evaluation functions, generative-based and matching-based methods. Generative-based methods leverage the generative capabilities of LLMs to directly generate evaluation metrics, assessing the quality of generated text through designed instructions. In contrast, matching-based methods focus on measuring the semantic equivalence between the reference and hypothesis texts, often using token-level matching functions in distributed or discrete string spaces. This categorization helps in understanding the different approaches to evaluating NLG outputs, each with its unique methodology and application. Figure 3 presents a comprehensive taxonomy of research in natural language generation, NLG, evaluation using large language models, LLMs. The taxonomy classifies relevant works into two main categories: prompt-based and tuning-based evaluation. Within these categories, methods are further divided into subcategories such as score-based, probability-based, Likert style, pairwise comparison, ensemble, and advanced evaluation protocols. This classification helps in understanding the diverse approaches used to measure the quality of generated text, leveraging the generative capabilities of LLMs. The evaluation of natural language generation, NLG, tasks using large language models, LLMs, can be broadly classified into two categories: prompt-based evaluation and tuning-based evaluation. Prompt-based evaluation involves guiding robust base LLMs to assess generated text through meticulous prompt engineering, while tuning-based evaluation relies on open-source LLMs that are specifically calibrated for NLG evaluation. Various scoring protocols are employed to judge the quality of generated text, including score-based, probability-based, and Likert-style evaluations. Additionally, advanced methods such as pairwise comparison, ensemble evaluation, and fine-grained evaluation are explored to achieve more comprehensive and nuanced assessment outcomes. Table 1 illustrates the various types of prompts used in evaluating the quality of generated text by large language models, LLMs. The first type, score-based evaluation, involves prompting LLMs to generate a continuous score reflecting text quality. The second type, Likert-style evaluation, prompts LLMs to assign quality labels based on a Likert scale. The third type, pairwise comparison, involves prompting LLMs to compare the quality of pairs of generated texts and determine which is superior. Each type of prompt serves a unique purpose in assessing the effectiveness and accuracy of text generated by LLMs. Table 2 provides a comprehensive overview of automatic metrics proposed and adopted for various natural language generation, NLG, tasks. These tasks include machine translation, MT, text summarization, TS, dialogue generation, DG, image captioning, IC, data-to-text, D2T, story generation, SG, and general generation, G. The table delineates the adaptation tasks, backbone models, scoring protocols, and evaluated aspects for clarity and reference. Evaluation aspects such as consistency, coherence, relevance, REL, fluency, FLU, informativeness, INF, semantic coverage, COV, and adequacy, ADE, are highlighted. The REF indicator specifies methods that are source context-free. This table serves as a valuable resource for researchers and practitioners in the field of NLG, providing a systematic guide for evaluating generated text across different tasks and aspects. Figure 4 illustrates an example of fine-grained evaluation, a method inspired by Jiang et al., 2023. This approach involves using large language models, LLMs, equipped with chain-of-thought, COT, prompting and a form-filling paradigm to evaluate the quality of generated text across various natural language generation, NLG, tasks. The fine-grained evaluation method aims to provide a more thorough and nuanced assessment by breaking down the evaluation process into detailed components, thereby enhancing the accuracy and reliability of the evaluation outcomes. Figure 5 illustrates an example of ensemble evaluation, inspired by Li et al., 2023c. This method involves multiple LLM evaluators with different base models or prompts, each evaluating the quality of generated text from various perspectives. Dynamic role profiles are generated based on input texts, and multiple rounds of discussions among evaluators are conducted to reach a mutual agreement on the pairwise scoring. This approach aims to synthesize the results of multiple roles as the final evaluation outcome, enhancing the comprehensiveness and reliability of the evaluation process. In the context of natural language generation, NLG, tasks, machine translation, MT, is evaluated using the Walmart metrics shared tasks, which include benchmarks for multiple language pairs and use a 7-point scale for human ratings. For text summarizing, TS, the SumEval benchmark is widely used, featuring summaries from 16 models annotated on a Likert scale from 1 to 5. Dialogue generation, DG, tasks are assessed through corpora like topical chat and persona chat, where responses are scored across 6 dimensions, including naturalness and coherence, with both turn-level and dialogue-level human judgments. Traditional evaluation metrics, such as Bielieu and Rouge, focus on exact n-gram matches, which can penalize semantically correct but lexically different hypotheses. These methods are simple and fast but not robust to paraphrasing. In contrast, BRT score measures quality through semantic similarity based on BERT contextual embeddings, effectively handling paraphrases and synonyms. However, Such matching-based evaluators depend on the quality of the pre-trained embeddings and may struggle with very fine-grained semantic distinctions. LLMs, on the other hand, have a strong capability for language understanding and generation, supporting evaluation without needing references. They can adapt to various domains and languages, making them suitable for a wide range of NLG tasks. However, LLM-based methods are computationally more intensive and require careful crafting of prompts, as variations in these prompts can lead to substantial differences in evaluation outcomes. Table 3 presents a comparative analysis of the performance of traditional and LLM-based metrics across three key natural language generation (NLG) tasks: text summarizing, sum-eval, dialogue generation, topical chat, and machine translation (WMT22). The table highlights the sample-level Spearman correlations for sum-eval and topical chat, and the segment-level Kendall-Tau correlations for WMT22. This evaluation is crucial for understanding the effectiveness of different metrics in assessing the quality of generated text. The metrics compared include traditional word overlap methods like BLEU and Rouge, BERT-based semantic similarity metrics, and recent LLM-based approaches. The results indicate that LLM-based metrics generally outperform traditional methods, demonstrating the strong language understanding capabilities of LLMs. However, the performance of LLM-based metrics can vary significantly, suggesting sensitivity to prompt crafting. In contrast, traditional unsupervised methods like Rouge and BLEU are more robust but generally less effective. Table 4 presents the efficiency comparison of various evaluation metrics by reporting the average number of texts evaluated per second. Traditional word overlap metrics like BLEU and Rouge are notably faster compared to LLM-based metrics. Specifically, LLM-based evaluators are approximately 200 to 400 times slower than traditional metrics. However, the efficiency of LLM-based evaluators can be enhanced using advanced language model inference tools such as VLLM. This comparison highlights the trade-offs between speed and accuracy in the evaluation of text generation models. The paper identifies several key challenges in the use of large language models, LLMs, for evaluation purposes. Firstly, the bias of LLM-based evaluators is a significant issue, including social biases related to race and gender, as well as order and egocentric biases. Secondly, the robustness of these evaluators is questioned, particularly due to the sensitivity of prompt engineering and the lack of resilience against adversarial inputs. Lastly, domain-specific evaluation remains a challenge, as general LLMs lack the specialized knowledge required for accurate assessment in fields like law, medicine, and finance. Addressing these challenges is crucial for the effective and fair use of LLMs in natural language generation evaluations. In this paper, the authors have systematically surveyed the role of large language models, LLMs, in the evaluation of natural language generation, NLG. They introduced a comprehensive taxonomy that classifies works along three primary dimensions: evaluation function, evaluation references, and evaluation task. This framework allowed for a systematic categorization and understanding of LLM-based evaluation methodologies. The authors also explored various LLM-based approaches, examining their strengths and comparing their differences. Additionally, they summarized prevalent meta-evaluation benchmarks for NLG evaluation. Throughout the study, the authors highlighted both the advancements and the prevailing challenges in this rapidly evolving field. While LLMs offer groundbreaking potential in evaluating NLG outputs, there are still unresolved issues that require attention, including bias, robustness, the integration of hybrid evaluation methods, and the need for domain-specific and unified evaluation within LLM-based evaluators. The authors anticipate that addressing these challenges will pave the way for more general, effective, and reliable NLG evaluation techniques, contributing significantly to the progression of both NLG evaluation and the broader application of LLMs. Thank you for watching.